जानवर लेके आए
Okay.
उन्हें उन्होंने चलान कर दिया उन्होंने अंदर
अच्छा.
So this next set is finishing up. We'll have some new data here pretty quick. Potentially hazardous asteroids can show up anywhere in the night sky at any time. So we're up here for 12 to 13 hours sometimes making decisions about the objects we're seeing, if they're real or if they're just noise in the background. And so the odds of finding an asteroid are going to increase as we move toward the east. Is fixed. 302. Oh, this might be something. Oh, you guys, look at that. Based off these 4 images, this is a brand new near-Earth asteroid. We got one. No, like I didn't think that was gonna happen. No, it's brand new. I just got the notice back from the Minor Planet Center that they published it. So there it is, bam, live. This is actually a big rock too. Right now, it is absolutely a potentially hazardous object. If you guys were gonna be here for a discovery, a PHA is definitely what you want. Yeah. This is a big rock. Yeah. It is nominally about 230 meters in diameter, which is quite large. And its minimum orbit intersection distance with Earth, which means how close it comes to the Earth's path and the Earth's orbit, is between us and the moon. It's only about 150,000 kilometers away, which is a significant PHA. A PHA like this only comes up a couple times per year. So these are the ones we want. Yeah, that's a nice one.
ਉਹਦੇ ਵਿੱਚ ਦਾਦਿਆਂ 'ਚ ਬੰਦੇ ਬੈਠੇ ਆ
When a 2-mile-wide fragment of the comet traveling 40 miles a second,
pieces of the comet that will hit Jupiter.
3 fragments are scheduled to hit the planet.
Will slam into the same area, the same spot on the planet Jupiter.
About 1993, we learned that there was a comet heading for Jupiter.
Comet Shoemaker-Levy 9 was a comet that was discovered by Eugene and Carolyn Shoemaker and David Levy. It was shown to be broken up into a bunch of pieces.
They traced back the orbit. This thing had gone by Jupiter and gotten disrupted.
And then they tracked the orbit forward and found out these are going to hit Jupiter.
And that got everyone excited.
It's really the first time that these impacts have been observed.
Impacts were very important in the formation of everything.
We could observe an impact on another planet.
Scientists still don't know what they're going to see tonight, but they do know that they've come to the best place in the world to see it.
The whole world community, scientific community, was preparing to observe these events.
Any telescopes that could observe the impacts did.
Many ground-based telescopes.
The Hubble Space Telescope.
All of the images from Hubble that went on the web or suddenly got everyone's attention.
Which was a real key to many of the scientific results.
Also Galileo.
Which was on the way to Jupiter at the time.
The NASA Infrared Telescope Facility had a campaign dedicated to observing Shoemaker-Levy.
This observing run for the Shoemaker-Levy 9 impacts, that was my first observing run ever.
We're starting tonight with the near-infrared spectrometer.
God, that's gorgeous.
We were seeing something pop up on the screen. We were just shouting. Literally dancing around. And we saw this bright thing just light up. And it was like, Yes, we did it.
We were all like kids in a candy store, I guess.
A lot of the energy we saw wasn't just the impact itself, but it was the sort of splashback.
And when those pieces plowed into the atmosphere, they brought up big plumes of material that rained back down on the upper part of the atmosphere.
So we're able to measure changes in the upper atmosphere of Jupiter.
It taught us a great deal about how impacts take place.
Scientists say if a fragment the same size hit Earth, it would leave a crater the size of Rhode Island.
It was one of those wake-up calls that, not only are impacts something that happened in the past, but they're happening now in our solar system.
And here it is, this awakening.
They kind of precipitated this NASA Planetary Defense Coordination Office.
To make sure to find the asteroids that come close to Earth and the comets that come close to Earth, get them cataloged, figure out where they've been and where they're going to be in the future, just so we understand, are we at risk of being impacted on the Earth?
So that's a big component of what NASA does now. It has planetary defense to find potential impacts of the Earth and protecting it.
Let's go back to Senator Cruz's question. What would an asteroid that is a kilometer in diameter, what would it do if it hit the Earth?
That is likely to end human civilization.
The impacts of Comet Shoemaker-Levy 9 with Jupiter in 1994, that showed us that, impacts are still happening in the solar system today.
That really spurred some interest on the part of the Congress.
NASA was tasked by Congress in 1998 to catalog 90% of all the large near-Earth objects, or those that are 1 kilometer or more in size.
Those objects are big enough to cause what we would call truly global devastation, meaning that they could cause global extinction events. The good news is that we found more than about 95% of them.
The catalog includes almost 900 asteroids 1 kilometer or larger in size.
That said, none of these known large NEOs pose any threat of impact to the Earth within the next 100 years.
And then eventually in 2005, that direction from Congress to NASA was set to find the population of asteroids that are 140 meters and larger in size that could do regional damage should it impact Earth.
A city killer. Now the picture's not so rosy. We know of about 40% of those objects today.
Today, we do not have a complete inventory of all the possible impactors.
And that is something that NASA and the worldwide planetary defense community has been endeavoring to do.
Well, here at NASA, what I lead is the Planetary Defense Coordination Office. We are helping to coordinate efforts not only in the United States and across U.S. agencies, but also around the world.
Finding asteroids, tracking them, calculating their orbits, figuring out where they're going to be in the future, studying their physical properties, and then you get that information you might need in the event an impact threat is discovered.
We've discovered more than 30,000 near-Earth objects so far, and we're discovering, hundreds, every year.
But we haven't found them all, so that's really the big question. There's almost certainly a decent-sized asteroid out there that is going to pose an impact threat to the planet. We're just trying to find it right now. So the way we approach finding near-Earth objects is basically just to make a short movie of the night sky that consists of 4 frames. And then our software will pick out objects that are moving inside of the 4 frames, and we have to identify if they are real or if they are false detections. I first started hunting asteroids in my backyard, and I just had the hope of maybe discovering one. And when that happened, it was a very special moment in my life. My interest in astronomy started at a fairly young age. I remember as a kid seeing Comet Hale-Bopp in the sky from southern Utah. It was really a spectacular sight as a child, and just trying to wrap my mind around what I was looking at was difficult. This is one area of science where discoveries are still happening on a nightly basis. And it's really a neat feeling to step into that, where you can be sitting at a telescope at night and discover a new minor planet that's in orbit around the sun that nobody has ever seen before. It's a special thing, and I think that's what draws a lot of people into this business.
The first order of planetary defense is finding the asteroids. And so one aspect of the program is funding institutions with telescopes that can image wide swaths of the sky to be able to look at the starry background and look for objects moving with respect to the stars to see if there's something there that we haven't seen before.
This is the whole sky. That's a whole sky camera. So you can see this is a live video feed from the end of the telescope, and you can make out the Milky Way right here. And this is the size of the images we're taking right now. And then we subtract the known objects and the stars from those images, and then we look for moving targets.
The object is moving because it's closer to the Earth than the background stars.
I can tell this first one is a star. You can see that object stays there. So if I load up a catalog image, which is a very old image, you can see that first hit is actually a star. That one's actually a star. Those moving targets are going to be asteroids that are in orbit around the sun. So that's a known asteroid. It comes up green, and it has the designation above it. And oftentimes they're new. We've never seen them before. So what we have here is a near-Earth asteroid that is likely brand new. And I can already tell that it's not coming up in any of the known databases.
And then what you have to do is go and identify whether it's a known asteroid or a new asteroid. So that's the next step.
When the asteroid is first discovered, we submit the information almost immediately to the Minor Planet Center at Harvard. And we are going to send this data off in real time here. The temporary designation we're going to assign to it, the date and the time, and the location on the sky that it was located, and then its approximate visual magnitude. I'm going to report it as a brand new near-Earth object candidate.
It's important to turn that information around quickly. The different survey telescopes quickly feed those position measurements to the Minor Planets Center, which is the internationally recognized repository for position measurements of small bodies throughout the solar system.
Minor Planet Center I like to think as the link between the astronomy community and everything that comes after that in planetary defense. My name is Federica Spoto, and I'm the project scientist of the Minor Planet Center. So part of the role of the Minor Planet Center is to actually distinguish what is known and what is not known. We keep all the observations and all the orbits of the objects. So we don't see the image, we just see these points, and those represent the different position of the object moving. And so it tells you very accurately the time of the epoch of the observations, and then the position. So once we have the position and the time, we can get the orbit.
So all the data comes in from everyone, gets consolidated there. So we have a common catalog that we are working from.
An archive of everything that is known and everything that is not known. The cool thing about the Minor Planet Center is that everything we do is public. So as soon as we receive the observations goes out.
That information can all be rolled up there and available for other observatories to see them and then go get additional observations so that there is enough information to get an orbit.
And anyone can then access that data to track these objects down and help us determine if they are going to be an impact risk in the future.
Once we find an asteroid and we've got an orbit for it, the next logical question is it going to hit the Earth? Fortunately, there's a group here at the Jet Propulsion Laboratory called the Center for Near-Earth Object Studies, or CNEOs for short, that is tasked with doing exactly this.
They assess the hazard potential of this newly discovered near-Earth object.
And they do orbit determination to see both short-term and way out into the future, 100 years into the future. Could any of those pose an impact threat?
My name's Ryan Park, and I'm the supervisor of the Solar System Dynamics Group at the Jet Propulsion Laboratory. And I'm also serving as the project manager for Center for Near-Earth Object Studies. So to date, we maintain about a little over 1.3 million objects, most of them being asteroids. We predict the motion of all known asteroids. And we process the entire data set from the Minor Planet Center to predict and reconstruct the orbit of the asteroids so that we can perform statistical assessment of the potential Earth's impact. Yeah, so what we do is we process the astrometry collected by ground-based observers, and we feed those through what we call the orbit determination process to get the orbit of the asteroid as a function of time. So we can propagate backwards, forwards, and figure out where the asteroid is in real time. So this basically catalogs all the potentially hazardous asteroids that might come close to the Earth, and we document the probability of potential Earth impact. And if it were to hit the Earth with certain probability, when is it going to be and where is it going to be? And we do this for next 100 years and assess whether it's going to be hitting the Earth, and if so, with what probability. And that information gets shared with the CNews website as well as with the entire world.
This data gets disseminated immediately to many different organizations, and NASA's Center for Near-Earth Object Studies runs watchdogs that are constantly ingesting this data and calculating the odds of an impact in the near future. And if they find that this object has any probability of hitting the Earth in the near future, we will get an alert on our systems within about 10 or 15 minutes.
And then when people start receiving this type of warning, then there's a huge community of astronomers that start observing it from all around the globe.
As the Earth rotates and nighttime falls across Asia or Europe.
And so we start getting observations from all over the world at every time, and we start processing them really quickly.
It's a very smooth running machine. It transcends boundaries of countries.
Asteroids don't care about international boundaries.
It doesn't matter where the asteroid impacts. It affects, the entire humanity. In fact, anything alive on the Earth.
It transcends basically anything except what makes us human and what it means to help discover and protect the planet from a hazardous asteroid that might be incoming.
Yeah, I'm really proud of it. I would say I'm proud, and I'm proud that I'm working on something that is actually very useful for the community. We're part of Planetary Defense, but also we do everything so that we can help the community.
It was a great honor to have an asteroid named after me. So there's Bryant Park asteroid. This was a huge deal for me. This basically led me to believe that I'm making some contribution to the field.
We didn't even know asteroids existed 200 years ago, and it's only been in the last few decades that we even had the technology to be able to detect these things. So, yeah, I might be referred to as the father of planetary defense. I created the term, perhaps, but it is only because I stand on the shoulders of those asteroid hunters before me that we are now able to protect the world from asteroid impact.
So this object has already been ingested by the Center for Near-Earth Object Studies Scout Watchdog. Right off the bat, it tells us that the probability this is a near-Earth object is already 100%. And the probability it is a potentially hazardous asteroid is 67%. There is no real impact rating or probability, so it's not currently a threat, but long term, after the arc is extended and we have a better idea of the orbit of this object, this might be a brand new, unknown, potentially hazardous asteroid.
So finding asteroids, that's probably the most important part of planetary defense, or the fundamental part of planetary defense. But it doesn't help to see an asteroid if you don't have enough information to know where it's going to be in the future.
You can't do anything about them unless you find them and know where they're going.
That means the race is on to try to figure out how can we get more data? Can we get more exposures of it so that we can figure out which way it's actually going? And then eventually get a really good orbit for it so that we can predict far into the future where it's going to go, especially with respect to the Earth.
So then there are telescopes that go zero in on those initial observations by the surveys, and they get even more measurements of those positions.
My name is Cassandra LeJolie. Spacewatch we're a follow-up survey, essentially. So the telescope behind me is a 0.9 meter telescope that we use to follow up near-Earth objects. When they're first discovered, they have very short orbital arcs. So they have very imprecise orbits. And so if we follow them up, we get a better orbit to determine if there's a higher chance of them hitting the Earth or not. So these are the type of images that we get back from the telescope. And so you can see that our asteroid is essentially a dot that's moving. And then the stars look like long lines because of how we track on the asteroid and not on the stars. When an asteroid is first discovered, the Minor Planet Center is able to calculate kind of a location on the sky where it should be. So we already have an idea of how the asteroid's going to be moving, so we take that assumed motion and move with it. So my typical day, or night, I guess, we typically observe for 4 to 6 nights straight, and we come up to the mountain, and we have dorms up here. So we stay up here the whole time we're observing. And what happens is that we'll open the 2 telescopes. We then have on our computers kind of a list of all the objects we can see that needs follow-up right away. There's a few objects we can choose here. I like to go for virtual impactors because they're top of our list. They have a probability of hitting us. We'll pick the best targets for the night. Some of them come in as we're observing overnight if they're newly discovered and they need follow-up then. So let's say I want to go for this object. What I would do is I would accept it in my queue, and then I would accept the value and send it for recovery. What that would do is that would move the telescope. So we get 3 images of it to see it move and to see at what speeds it moves. And then we measure its location on the sky. That is the measurement we report back to the Minor Planet Center. Well, that's an asteroid right here. It's really cool when you're looking like at an image from the sky and you see a moving dot. Like every time I find that moving asteroid, I'm excited by it because it means you found it. Like you found a thing in space that is moving. Like it's right there on my image. I can see it. So right there is our object and it's moving right there. So the first image is in the star, so we can't measure that. But then the second and third image are right there. So we can actually measure those. And that new measurement then helps better predict the orbit fit and thus better predict where it would be in the sky next time someone needs to observe it to follow it up.
The most important thing is always get more data, because the more data you get, the better you are at finding the orbit and know where the object is.
And if you take another image a little bit further, you can then put another data point, and then you can keep tracing that orbit around.
As you collect more observations, the orbit of the asteroid in question will get better and better.
I really like that I'm protecting the planet. And yes, I'm not the one that's like with a cape pushing the asteroid away. That's not what I do. In some ways, like my little contribution might help not just myself, but someone in the future. And I think it's very important to do that.
So last night, while surveying in an area of the sky where we don't typically find a lot of objects, I discovered an object that had to be fairly large to be visible for where it was in the sky.
So here is the asteroid that Catalina Sky Survey discovered a few days ago, and we can also tell that it's a pretty big object.
The asteroid has to be observed for many weeks and months into the future, so we can extend that data arc.
So the orbit of that potentially hazardous asteroid is known into the future.
So the discovery arc of the asteroid consists of just 4 points of data over 20 minutes, and that is a really small snapshot of the entire orbit of the asteroid.
And it was able to be followed up all around the globe so that we didn't lose that asteroid. And you can see that it's been followed up by several different telescopes right here. So the arc length means it's been observed for more than a day. So that is where it comes the closest to intersecting the Earth's orbit. And telescope around the world will continue taking observations of this object to keep seeing if it has a potential of hitting the Earth or not.
Well, at the current rate of detection of near-Earth asteroids, it's going to take us about another 30 years before we'll have this catalog that we've been tasked by Congress to do.
We've only discovered less than 40% of the 90% of the object we need to discover.
Finding the asteroids isn't something that can just happen overnight, because telescopes can only see so far away, or they can only see so faint into what they might be looking for out there.
Ground-based telescopes are kind of limited to looking at night, away from the sun.
And we have to wait for the solar system to bring asteroids around. The Earth is traveling around the sun, the asteroids are traveling around the sun, And so it isn't possible to see the entire solar system at the same time.
It's hard to find asteroids because relative to the size of the Earth and the distances within the inner solar system, they don't get bright enough to spot until they get closer to the planet.
One of the tricky things with searching for near-Earth objects is that some of them are extremely dark. They're darker than lumps of coal. And that means that when we look for them using the sunlight that reflects off their surfaces, they're actually hard to spot because they're dim and faint.
There are asteroids out there that are very darkly colored and don't reflect a lot of light from the sun, and so they're difficult for the telescopes on the ground to discover that are looking at the light that we can see with our eyes.
So how do you overcome this? We have to go into space. We have to use different wavelength than reflected light. All the telescopes on the Earth that are currently finding near-Earth asteroids are discovering in the visible wavelength. They are primarily looking at light reflected by the asteroid from the sun. The sunlight hits the asteroid, reflects, just like everything in the solar system.
One way we can kind of get around this is instead of looking at the sunlight reflecting off their surfaces, we can use the heat that they emit to search for them. If we have a heat-seeking telescope working at infrared wavelengths, even the dark objects just pop right out. They stick out very brightly because they've got a lot of heat that they re-radiate, and we can see that energy.
Once you go into space, you're away from the heat of the Earth, you can start looking in the infrared wavelengths. Because in the infrared wavelengths, asteroids have more energy being given out because a lot of them are darker, so they absorb the radiation in the daytime, and in the nighttime they re-radiate. So they're very bright. You don't need that big a telescope in space to detect the asteroids that you would from the Earth using visible light. And Near-Earth Object Surveyor is one such telescope.
The Near-Earth Object Surveyor mission, or NEO Surveyor for short, NEO Surveyor, is a space telescope that we're building that's designed to detect, track, and characterize asteroids and comets that have the potential to get close to the Earth.
But it'll also be positioned in such a way that it can survey closer to the sun than the telescopes on the ground.
Because of this nice tall sunshade, we can actually point relatively close to the sun, and that lets us look far across the solar system so that we can spot the asteroids when they're far away from us.
So that, working in concert with the telescopes on the ground, is going to really accelerate those objects getting into the catalog.
With NEO Surveyor, we should be able to see something like a few 100,000 new near-Earth objects over the course of its survey.
We expect the numbers will increase by somewhere between a factor of 5 to 10 in the